All right, welcome back to System Software. So as I said before, this is the last lecture. We're going to go over, last lecture of this class, we're going to go over the final exam. And just to reiterate, it is in person. You must take it in person or at SAS. And you can take it on web courses on your laptop, your own personal laptop, where that's the only thing you have open, and we'll be proctoring to monitor this. Or you can take a paper exam. I'll bring paper exams. Make sure you have your UCF ID. We'll confirm your ID when you enter the room and check you off. The laptop is the only device you can have. If you need notes, bring paper notes, just like with an in-person exam. So it's just like the in-person paper exam, except the exam sheet and the answer sheet are replaced with web courses. But everything else is identical to the midterm. So same amount of physical pages. Any worries about the amount of physical pages? Do you want more because it's a slightly longer exam? Yes, more? All right, so since it's 16 to 24, this will be 8 to 12. How about that? 12 for 24. Well, 24 sides, 12 pages. So that's 50% more. The exam is 50% more, so let's do it that way. So I think that should be plenty. You can probably copy most amount of reference material that we have in the class. So you will need more if you want reminders on assembly code and SimpleIR. It's not going to be very different from the code we saw in class. So you could take examples down, little explanations, practice with the different move operations. But there's a small finite number of assembly operations that you need for the class. Yeah.
There's probably no we're doing it like you wrote the equation, right?
No. You won't literally be writing. Yeah, I'm only asking you to do kind of hand translation, or let me go over the topics when we're done with logistics. Any other questions on logistics? So it's just like the midterm, in person, but you can take, instead of the paper, you can use web courses, and web courses only, and nothing else on your laptop. Everything else is the same. Paper notes, although it's 12 now. Is this updated? 12. Now it's updated. No putting answers on your pencil or writing implements, which has actually happened before. Actually has been used for SAT cheating, where they have answers on a pencil. So no additional information besides your notes. So it's 24 questions, and the final's worth 16 points, so each question is worth 2/3 of a point to make some annoying fractions for grading. More than half are multiple choice, and then we have short answer and long answer. So let me go over the exam. So I should say also that the long answer ones where you're doing coding, these are all new content. So you won't have to do system call programming. Those will be multiple choice. So don't worry too much about being able to write systems code. Let me just double check to make sure that I'm not lying. Yeah, you won't have to write systems code like you did on the midterm. It'll be multiple choice questions about systems code. That's for the long answer ones. There may be short answer ones on the midterm. Okay, so let's go over content. So file systems and navigation. Why is the Unix file system hierarchical? What makes it hierarchical? Yeah.
Everything is saved below the root file. From there, you can have files that are other directories that contain other files, and it grows down.
Yeah, so directories. And now, what are directories? How are directories represented in the file system? Special files, yeah. Directories are also files, right? They're also files. They just happen to contain a mapping of names to other files. That's what makes it hierarchical. Absolute versus relative paths. What's an absolute path? Starts at the root. Otherwise, doesn't start at the root. Working directory. What's the working directory?
Directory you're in?
Yeah. What's it? Yeah, directory you're in. Well, more specifically, it's the directory that the process is currently in. So when you're in bash, the bash process is running, and the kernel maintains the state of what directory you're in. How do you change the working directory? CD and bash. What about in a system call? How do you change the working directory?
CHD.
chdir, right? So there's cd in bash, chdir in the as a system call. So another, for that's processes. How do you rename a file? Yeah, move mv. What will show you the text of a file? This should be Unix standard utility. Yeah, cat. How do you delete a file? Yeah, rm, remove. Okay, so some basic multiple choice stuff for file systems and navigation. No, big syscall implementation for files. All right, version control. I hope everyone has learned about version control, because if you're going to be a software engineer, you will absolutely use version control. And I know it was probably very frustrating to do this on the command line and learn about it and have merge conflicts and learn about distributed version control. But let's go over some core questions for version control. So how do you copy commits from the local repository to the remote repository?
Git push.
Git push. Very good. How do you copy commits from the remote repository to the local one? Yeah. Pull. What Git command stages a new file? Yeah. Git add. Good. Git add. And what Git command creates a log of the change to a staged file to the local repository? Yeah. Commit. That's commit. So remember, there's 4 pieces. Okay. There's 4 pieces: working directory, staging, local repository, remote repository. Working directory to staging is add, although if you do commit, it'll also add for you. And then commit does staging to local, and then push and pull go to and from remote repositories. Let me make sure I'm not missing anything. All right, so that's version control. Any questions on version control or any of these? I think you've all used version control. You hopefully know at a fine-grained level the difference between commit and push and how that affects your local and remote copies. And I've actually gotten feedback in comments from many people like, I'm glad we learned Git now, because very few people use it in class, and they used it at their internship. They were sort of benefited from it, so I hope that at least helps you. All right, processes. How do you redirect standard I/O from a bash command to a file? Yeah. Yeah, it's the angle brackets. So the kind of mnemonic for this is, think of it like an arrow. So if the angle brackets are pointing to the file name from the process, that's redirecting output to the file. So think of it like an arrow pointing to the file. And if it's the other way, pointing to the command name, instead of using vague hand gestures, let me show you what it actually looks like. So for instance, if I have ls to out file, this kind of looks like an arrow pointing to the out file, right? So it's writing to the out file. It's taking the standard out, writing to the out file. If I've got cat in file, arrow is pointing to the program, so you can think of that as input to the program. Yeah?
So for this, would it be grep greater than sign grep.txt?
Did I give an example? Yeah, grep. If I want to redirect greps out into the file, I don't know what I said, out in, to the file grep. What do I type? Yeah, so if you want to go out, if I want to grep, well, for a real grep command, I'd need to have some input to it, and I need to match something like hello. This would save the results of grep's output. I could also search for hello in a file, and that will take the input to grep from grep.in.
Can you put the hello in quotes?
You don't have to if it's a single word. Yeah, this is nitty-gritty details of bash syntax. Definitely not going to make you understand this, but quotes will turn something with spaces into a single argument, basically, is what quotes will do for you. But yeah, there's a lot of gnarly details to bash is parsing. How do you redirect standard out from one command to another command standard in? So let's say I want to have find and then count it with WC. Yeah. Pipe character, yeah. So this is equivalent to doing this. This pipe is like doing this. What's that? Shorter, and you also don't need to have a file stored to disk. Yeah, or well, there's still two commands being run, but the pipe is a file, special file. Remember, a special file that's created in kernel, managed by the kernel memory to basically make a temporary file for you. So actively, yeah.
So you have to put something else in find, right?
Actually, no. The GNU utility, you can just run find by itself. I think if you're on Mac and you tried to type find, it probably complained, I think, because it's a BSD version and you need to give an argument for whatever reason to the BSD version. But no, you can run find by itself and it just does the current directory. So if I run find, it just gives you everything in whatever the current directory is. All right, editor. How do you edit files in Vim or Emacs? Yeah.
Vim space the name of the file.
Yeah, that's how you edit them. How do you quit the editor? :Q for Vim. If you want to write the file, :WQ. What about Emacs?
So when you
Oh, yeah.
say edit files, you mean like getting into the editor?
Yeah. Control X, Control C for Emacs. So okay. Yeah, I'm not going to ask too much about editors. Maybe there'll be a freebie in there. Okay, processes. So this is like from the midterm. How do you create a process in the Unix system call world? Let's get, yeah.
Like fork it and then execute.
Well, yeah, well, you fork, and actually, as soon as you fork, you've already created a process. You don't have to exec it. But how do you, execute a program with a Unix system call? Exec. So what does exec do? Yeah.
And process executes a command.
Well, that's at a high level, but what does it do to, Yeah, it changes the running program. So if remember, the running program is loaded into memory in the text segment, or that's in the executable file, but it's literally the machine code of the program is in memory. Exec overwrites it with a new program and then starts running it at the beginning of the program. Yeah.
Do we need to know the different types of exec?
No, don't worry. Yeah, don't worry about that. You can always run, you look at the man page for that. How do we redirect system calls, or how do we redirect standard out, et cetera, using system calls in a program? Yeah. Dupe. Yeah, dupe or dupe 2. There's also dupe 3, I think. But yeah, the dupe command does that. What do pipes do? The pipe system call? I think we just described it. Yeah.
Lets you read and write to a file with 2 file descriptors for rewriting.
Yeah, it creates like a kind of a temporary file for you in memory that you can read and write to from 2 different file descriptors. It's like a sort of a one-way queue almost. Okay, so I think that's, let me see if there's anything else on processes. Oh yes, okay, yeah, that's the other category. I think that's everything for these categories. All right, source code versus executables. I think this had to be a little compressed due to the hurricane stuff. But okay, so you have source code, you have a C file. How does that become a running program? How does it become an executable? How does it become a running program? Yeah.
It's like that whole flow chart thing.
Yeah. Do you remember the pieces of it at all?
There's like an object file, I remember.
Yeah, go ahead.
Kind of going back on what he said, basically he has to compile it so that we have a main.x or assembly code, and that assembly code becomes linked to other, I think, libraries and other things for the main file, and it basically reads the,
Yeah, the program binary, reads the program binary. And that's the exact part, right? That's how it becomes running. So you got the preprocessor, which we didn't talk too much about. Then the actual compiler, which goes to assembly. Assembly goes to an object file, which is the machine code version of assembly. Then the linker, as your classmate said, combines multiple object files, combines multiple compiled C files, because you don't have to write the entire program in one C file, and you might have libraries, like standard C libraries. Then that's what gives you an executable file. Once you have an executable file, the loader in the kernel, which is invoked with one of those exec variants, turns it into a running program by overwriting that machine code, that program binary, in the current memory of the currently running process, and then change the program counter to the beginning of that machine code. Questions on that? So just remember, compiler goes from C to assembly, assembler goes from assembly to machine code, and linker merges multiple assembly files. Yeah?
This is kind of a random question, but does that mean like when you close a program, it doesn't like delete the actual like executables that are loaded into the RAM? It'll just wait to override it?
I mean, technically, yeah. Like if you mean into physical RAM.
Yeah.
Yeah, it's kind of the same way storage works.
Like if you close the program and then immediately relaunch it, it just like launches really fast.
Oh, yeah, that's a feature of the kernel where it will. Yeah, I think it will actually. Actually, is that right? I'm not sure if that's for a program. I think that's the case, but I'm not sure. Oh, that actually just might be because when it was loaded from disk, it might have been the disk that was cached, so that file stayed mapped into memory. I think that might be what's going on. It is the case that libraries are shared between processes. So if you load one dynamically loaded library in one process and then use it in another, I think the kernel also has features to make that sharing, make that faster. But yeah, sorry, I don't have more detail. All right. Oh yeah, and then the Unix utilities. So what's the utility for linking called? If anyone remembers, yeah. What was that? It was close. It was L. It starts with L. So it's LD, which is it's like a misnomer because I think it's supposed to be an abbreviation for loader, but actually it's a linker. It's not a loader. Assembler is AS. Compiler is GCC. And then I'm not going to ask about this, but the C preprocessor, it actually has a separate utility called CPP. Doesn't mean C++. It means C preprocessor. But I'm not going to ask about that. But just know that the compiler, all the compiler does is produce assembly. It's the assembler that produces machine code, and the linker that combines those individual object files. All right, I'm not going to ask you too much about that. All right, so let's get into the bulk of the final. All right, so SimpleIR, what kind of instructions do we have in SimpleIR, if you know from memory? Let's name them, I guess. Yeah.
Assign variables and stuff.
Okay, assignment. Anything else? Yeah. Yeah, the pointer operations, deref, ref, assign deref.
When you say instructions variables, you know, like what type of?
I guess the statements you have in the language, or the constructs. Okay, so that's good. You got 3 more. Let's give someone else. Yeah, go ahead.
Arithmetic
Got our arithmetic operations. Yeah.
and calling functions.
Function calls. So you can see the whole grammar in your project. And so hopefully you learned a little bit about the set of constructs. So you can either use the grammar, which might be less readable for you, or just have an example program. There are several example programs, so you can define functions. And let me show an actual example of code here. Let's look at my malloc program. So this contains a couple of examples. So you can declare the function, you can declare local variables and parameters, you can set a return value, you can do arithmetic operations, function calls, dereferences. So I don't know the best way for you to remember all that, but it's just like in assembly. You know, you have, and I broke it down in class into these categories like functions and function calls. Local variables are part of the function definition. Function parameters part of function calls. And then these are the operations that you have: arithmetic operations, branching operations, pointer operations. Assignment we covered in local variables, but those are like kind of the 4 categories of operations you have. Once you define the function, you can do assignment, arithmetic, branching, and pointer stuff. So I'll have a question that asks you to write a SimpleIR program. So hopefully that won't be too bad. Yeah.
One of those simple IR functions, do you want it to be able to like branch the entire like stuff in here, like local bars?
Yeah, ideally. Yeah. I mean, you can just have like put an example program in your notes, and that should I think that should help, right? So yeah, I'll ask you to write a SimpleIR program. Let's see. So yeah, be able to write a small SimpleIR program. You know, use branching, use assignment. You know, if you've done MIPS or assembly, it shouldn't be too bad. It should be easier, I think, right? Now, if you get like little syntactic errors, that's fine. Just have a couple of example programs. Like I think I even had a homework question where I asked you to write a SimpleIR program. So just review that homework, review all the examples we have in class, and with 3 or 4 examples, you'll have the whole language, examples of the whole language. All right, questions on that? Questions on SimpleIR? So it's just like the homework where you have to write a SimpleIR program. Yeah?
How come in that malloc function you did 8 integers, but then you only need 1?
Because I just didn't write the code to like do the pointer arithmetic, but you totally could just like, you know, start doing pointer arithmetic here. But I really just wanted to test to make sure I could actually call malloc correctly, which is very exciting to actually get malloc code and be able to play with pointers. All right, so functions, we went over this a ton, the stack frame stuff. So you should definitely know what's in the stack frame. So what is in the stack frame? Yeah.
The return address, RDP, the base pointer, and if you have any local variables, you do parameters. And then
parameter,
you
yeah.
also have, I think that's it.
So return address, old base pointer, you said, local variables and parameters.
Right.
What about the order of those? What's the order that they're going to be from high memory to low memory? Yeah.
They'll be opposite. I know like some parameters go like above the RDP, but then like some go below. It's easier with that diagram.
Yeah, the diagram is in here somewhere. So you can use this diagram. This is the high address, stack grows downwards. So what's the first stuff in the stack frame? Yeah.
The 3 6 parameters are saved in special registers, and the other 2 are pushed.
Okay, so this is what's not in the stack frame. The registers, the first 6 parameters are in registers. Remember that? In this ABI, and I'll actually specifically say System 5, AMD 64 ABI. The rest of the parameters are in the stack frame. I know for a lot of our examples we didn't have any parameters in the stack frame, but they're going to be there for whenever you have more than 6 parameters. So parameters come first. Remember we're growing downwards our stack, so the first things pushed are the parameters. Who pushes those? The calling function or the called function? Calling function, yeah, the caller. Then we have return address, old base pointer, local variables. Okay, so epilogue. What does the epilogue do? Yeah.
It's based on a stack frame that the call is kind of set up. So basically, it sets the stack pointer back up to
So it tears down what the callee set up. So it tears down the locals and the old base pointer. And yeah, the way we did it was we just set our RSP to be where it was before we had the prologue, which is at the return address. So that's what the epilogue does. Okay, so these are a little subtle, and I think and I do ask questions about these. So the difference between SimpleIR function calls or function definitions versus assembly function definitions. So the assembly call instruction, what does this do in the machine? Yeah.
So it both sets the return address and then it branches to the call function.
Yeah, it sets the return address, or it saves the return address, and then just branches. It just jumps to the function. And what about the return instruction? Yeah. Yeah, it does kind of the opposite of it. It pops the return address and branches to that. So how does that differ from a SimpleIR function call? So in SimpleIR function call, what happens in the function call for SimpleIR?
Go to.
Yeah, what's that?
Go to.
So you're saying the SimpleIR function call just does go to, and that's it?
To a particular segment of the code, yeah.
So let's look at the function implementation section, or do I have function parameters? So if I've got a call here in SimpleIR, what does this do at the assembly level? Well, where's the assembly code? I think it's probably better to look here, the full example. So if we have a function call like here, a lot more is happening than just branching. We have to set up the stack frame, right? So we have to pass all the parameters via registers and the stack, do the assembly level call, which doesn't just branch. Remember, it saves the return address and doesn't branch. And then when that call happens, the function prologue gets executed, which sets up the rest of the stack. So that's the first part of what a SimpleIR calls. The same thing that happens in C. So the difference between a high-level function, a kind of a real function or programming language function, and an assembly call is that an assembly call is just a branch, whereas in a C function or a SimpleIR function, we're implementing what you might call true functions, functions that have function local state. Because remember, if we tried to just do a branch for, say, a recursive function, we wouldn't necessarily get the result that we wanted. That was that whole lecture on what happens when you do factorial with static or global data. My version of factorial didn't work as expected because we don't have function local state. And one of the main purposes of all of this, the stack frame setup, is to implement functions with function local state, which a simple branch won't do. Does that kind of make sense? Questions on that? So call instructions. So yeah, remember what call and return do in the assembly level, and just remember function local state, how this is managed. It's managed with the ABI, which tells you how to pass parameters, tells you how to set up the stack with the prologue and epilogue. And that's what makes these kinds of functions, these programming language functions, different from assembly, simple assembly branching. So yeah, remember how parameters are passed. First 6 are passed with registers. Any others beyond 6 in this ABI are passed by being pushed onto the stack to start constructing the stack frame. So yeah, remember that. Remember how callers pass parameters. Okay. So variables. I think we went over this quite a bit. But let's go over how variables are accessed. So if I have, say, let's go back to local variables. Those are pretty ugly. So if I say assign x to 11, how does the state of the machine change when you assign to a variable? Yeah.
You do 11 in the RAX, and then you do use the offset of the base pointer and assign that from RAX.
Yeah, so remember at the assembly level, there's no notion of symbols like x. So the compiler maintains an offset from the base pointer and uses that at runtime in order to compute what address the machine computes for you, what address to store into. So variables are assigned and read from by translating variable uses into offsets from the base pointer. Yeah.
It's always 8 bytes, right?
For SimpleIR, it's always 8 bytes. Yeah. For our language, SimpleIR. That's not the case for all programming languages or for C. It's not the case. So this is covered in local variables, how this gets stored, how they get translated to assembly. So this was our translation from assigning x equals 1 to the assembly code. So what does this mean? What is this? Yeah.
They're going from that's storing RAX into the X is the offset -16 RPB, correct?
Yeah.
So basically you're storing the value that's stored RAX into X, which is offset -16 from the base.
Yeah, so you're taking whatever's in RAX and storing it into the memory address that's held in RBP -16. And why is that X? Yeah.
Because you say the name of the variable as an offset. Right?
Yeah, so in the compiler, you map, where did I put this? In the compiler, you map, I thought I had a table. I had this somewhere. Yeah, in the table, in the compiler, you keep a table that maps the name of the variable to an offset from RBP. And that's how variables are translated to assembly, to locations in the stack frame. So that covers the symbol table. Immediate values, this is using this syntax. Oh, that minus should be there. Versus this syntax, immediate versus stack frame loads. So assembly instruction support for accessing variables with the stack frame, that's just this special syntax for loading and storing from offsets from RBP. So I think I went over that quite a bit. I hope that has stuck a little bit. But just keep some examples in your notes, little reminders of what the assembly code looks like, so that you can. So I'll ask you, I think a couple of times. Let's see. So I'll at least ask you at least once to write assembly code for at least a piece of SimpleIR. Yeah, so I'll ask you to write a piece of SimpleIR. So So for instance, for arithmetic, what x86-64 instructions are used for arithmetic operators? We have plus, dash, slash, and star. So what x86 instructions corresponded to each of those? Yeah.
Add, multiply, divide.
Yeah.
Add,
Add, mult,
Sub.
idiv, add, sub, mult, idiv. This was all in the lecture on arithmetic, where each operation is listed here. So add, sub, mult, imul, integer multiplication, and idiv for division. I'm not going to ask you to do the division because it's just kind of annoying in x86. All right, so that's arithmetic. Yeah, just remember that in so for instance, in SimpleIR, we have 3 parameters to an addition. We have the left and right operands, and then the variable to store to. But in Intel, there's only 2 arguments. So what is the meaning of this? Yeah.
Move the value in RBX to RAX.
Well, it doesn't move it, it adds it.
Adds it.
Yeah, it adds it and then stores the result in RAX. So just a minor difference between x86 assembly. I was actually looking at RISC-V, which actually looks a lot easier to compile to. So I maybe not next semester, but maybe next year I'll actually try RISC-V or some ARM instruction set. It doesn't have all this complexity. They actually have 3 argument additions, so maybe that'll be easier. But anyway, we've done Intel x86 here. So just keep notes, keep examples of these handy. All right, any other questions on arithmetic? Yeah.
What if our use is not initial?
Well, it's always initialized. It'll always have some state. I mean, I guess when you start the machine, I don't know if it's initialized to 0. It probably is. So it'll always have some value. Not initialized means, it's just like in C, if you don't initialize a variable, there's no guarantee about what data you're going to get. So it'll just be whatever you had previously set it to. I don't know if it gets zeroed at the start of a program. I doubt it would hold the data from a previous process. I guess it might get zeroed, but I don't know. But in the course of your program, if you haven't correctly translated SimpleIR, then RAX may hold some data that doesn't actually correspond to the thing you're trying to add. So there's no real notion of uninitialized data. The registers always hold some value. All right, any other questions on arithmetic? So yeah, I'll ask you, let's see. What are my questions on arithmetic? So I may ask you, which instructions are used for SimpleIR. For variables, I may ask you how to use a move operation. There's various move operations. There's move immediate. There's move to and from a variable using that offset syntax. And then there's also, we'll get to it, but there's also pointer moves. That's stack frame question. Parameter passing question. So I may ask you to look at a snippet of SimpleIR and ask me, have you tell me what the value of a variable is. This is like semantics of SimpleIR. Yeah, there'll be some of those, just being able to look at SimpleIR code and understanding what it means. I'll ask you to do one question, very simple assembly to turn it into SimpleIR, kind of decompile it. But it should be a very simple one. Yeah, I'll ask you to write SimpleIR. Okay, so I'll ask you to draw out a stack frame for a particular function. So, you can just list it. You don't actually have to draw it.
How would we list it?
Just in a list. Just like, I think, you can just put it one line at a time, or you can use dashes. Either is fine. I'm also going to ask you to take a C program and write SimpleIR for it. So that'll be a tricky one. But we covered that couple lectures ago. And write some assembly code for a SimpleIR program. All right, let's look at branching. So branching in SimpleIR, you've only got two types of branches. You have if gotos that look like this, and you have unconditional gotos. In assembly, how did we do conditional gotos, if you remember, in assembly? Yeah.
Is that like all the jumps with the LED and whatnot?
Yeah, the different variations of jumps. So you have to first do compare, CMP, and then that sets this hidden state in a hidden register. And then you just use the jump corresponding to whatever you want to test. So if you're trying to do RAX less than or equal to RBX, then you do compare RBX, RAX, and then do jump LE. So why does this correspond to RAX less than or equal to RBX? Because in this syntax, the second operand is the left operand, just like in addition and subtraction. So for instance, here we're asking for x less than or equal to 10. We put x, this is x's value in RAX, 10's value in RBX. I'm not going to be too super nitpicky if you make these little mistakes. I know these are annoying details of x86. Yeah.
I'm back in there.
Okay. You raise your hand again. So yeah, just remember that you do CMP for compare, and then pick whatever jump command that corresponds to the condition that you like to test for. Yeah.
So if we're doing like not less than 2, if RAX is not less than RBX, should we flip it then?
Yeah. Yeah, you would just invert the condition. Yeah. Yeah, but SimpleIR doesn't have a not relational, right? It only has these SimpleIR. These are the only operations you have for if gotos. So do your best on the AT&T syntax. I know it's confusing. Just have examples of the translations between SimpleIR and AT&T syntax, and I think that should give you enough material to answer some of these. So this is a good question. So how do we implement if, while, and for? So for instance, if, how do we implement if in SimpleIR? Well, it was a little trickier than that, if you remember. So if I have if x less than or equal to 10, then x equals 3, let's say. How would I write SimpleIR to do this same thing? Or just a snippet of code. Well, I could say if x less than or equal to 10, go to some label. But what was the challenge of doing this? If I set x equals 3 to here, well then, yeah, you could do it this way. And then have an unconditional go to here to get past that. But that was the main point, that if you don't have this go to, both branches are going to set x to 3. So you can either write it this way, or you can invert the condition. Well, let me not make this confusing. I'll just say another label, which maybe is confusing too, I don't know. And so this is the branch that skips the body, and then this is the body, so x equals 3. Any questions on this? I think we went over this for almost a whole lecture, right? Like half a lecture, how these translations work. There'll be one question on this where you'll have to do this translation. Just one. Questions on this? I can't tell if this is all review for you, or you're just completely confused and blanking out on the whole second half of the semester, which I hope not. And we talked about this. Use compare and jump with the condition code, like jump LE, jump L. So just bring notes on this. You got 12 pages. You can bring notes with examples of IR, examples of assembly, And there's tons of translation examples. Well, maybe that makes it harder, but take a couple of these representative samples of translations to help you during the exam. All right, questions on branching? And then we come to my favorite part, pointers, the most confusing part. We went over this, I think, also quite a bit. We'd spent 2 lectures going over pointers. They are confusing because you have to keep in mind the distinction between the variable's location in memory and the value of the variable which holds a location, the value of the variable holding a location. So I think this example that I went through last time illustrates quite a bit of this. This was for assignment. So let me check the questions here. So what does this register indirect move do? What does this syntax mean? Yeah.
Address RX.
Yeah, so take whatever the data in RBX is, don't copy it to the RAX register, but instead look at the address that's in the RAX register and do a store of RBX to that. What's that? You can think of this as a dereference. Yeah, this corresponds to a dereference. A dereference assignment. Exactly, yeah. So the full translation of this first populates RAX with the value of because remember this is a deref assignment, so it takes whatever the value of T1 is. That's we want to store to that address because we're doing a dereference assignment here. So we take the value of that address or take the value of that variable and we store to it. Questions on that? So we went over that quite a bit. All right, so this is all the topics in the final exam. So there'll be, let's see how many questions on the pointer stuff. There'll be a couple. There'll be one where you'll need to write assembly code for SimpleIR code that does some pointer operations, just to make sure you grasp that. There'll be some writing SimpleIR code for like a if or a while construct. They'll be writing x86 code for some branching or arithmetic SimpleIR code. And there'll be some questions on writing like a SimpleIR program. There'll be a question on writing a SimpleIR instruction that is a possible decompilation of some x86. I tried to make it very simple, so don't worry too much about that. If you know how to go from SimpleIR to x86, the decompilation shouldn't be too hard, I hope. And then, all these conceptual questions about the calling convention, arithmetic operations, branching operations in x86. Yeah.
See the SimpleIR code for the branching operation again?
Yeah. SimpleIR code, yeah. So there's an example of SimpleIR code. This one doesn't have or I guess I have an example here too. Not here. This is a couple of examples. This is an example of some branching SimpleIR code. Yeah.
Will we have questions where you ask us to convert from a SimpleIR to C source code?
No, I won't ask you to decompile SimpleIR to C. There's one question on decompiling x86 to SimpleIR, likely SimpleIR. And SimpleIR to assembly, yeah. And there's one question on C to SimpleIR, which I know we didn't cover extensively, but it's like an example we did in class.
It's like the one you just did, right?
Very similar to the one I just did.
Can it be assembly code?
For this one,
Yeah.
I didn't write it, but we can try to write it. Should we do some assembly code for this? Okay. You're stretching my assembly skills. So I'm just going to assume X is in this offset from our -8 from RBP. All right, so let's do this one. So if I make errors, I'm not going to penalize you for those errors, but it'll be something like, well, okay, we got to set up 2 registers for ourselves here that contain the values we want. So I'll put the left one in RAX, and I'll put the right one in RBX. This is a immediate store or immediate load of 10 to RBX. All right, so now RAX contain our they contain our operands for our if goto. So I want to compare these two. So I'll compare. Remember, the arguments are like swapped in the AT&T syntax world, and then I'll do a jump less than to some label. So let's put our label down here. Our unconditional gotos are much simpler to translate. It's just taking goto and using the Intel unconditional goto, which is JMP. And then here we've got an assignment. So there's several ways to do it. So you could do the immediate, like I'll do how my compiler works. I put the value I want to store into RAX. So I'm taking 3 and putting it into RAX. And then I do a store to the memory location associated with X, which is what? What's the operand for that? Okay, good. Not losing everyone. And then we've got our skip label, and that's the assembly code.
Great. And you don't have to.
Yeah, I didn't do the full program. I think I ask you to do a. Do I ask you to do a complete program? No, I don't make you do it. Yeah, I don't have you do a complete assembly program because it's just kind of a pain, with the pseudo ops and the prologue and epilogue and everything. Just know what the prologue and the epilogue do. I'm not going to ask you to write a complete x86 assembly program because it is kind of a pain.
Wait, in the exam, are we gonna actually write the assembly? Okay.
Yeah. So in web course, you can put it in a web courses box and actually type it out,
Okay.
or on paper write it out. This shouldn't be too long. I'm trying to see what the maximum length here. I haven't worked out the maximum length. You have almost 3 hours for the exam. So, and there's only 5 of these open-ended ones, which are all some form of writing SimpleIR or assembly in different ways.
So what's the short answer? Just kind of other stuff.
It was like on the midterm, what does this x86 instruction do? Let's see what else we have. Writing, it'll be like something I think you can do on a single line or describe in a sentence or two. That'll be the short. So there's 5 of these. There's 5 of these long answer ones. Yeah. It did, but I didn't need it anymore after I. It didn't hold the address. It held the value of X, but I blew that away because I didn't need it anymore. Oh, we never store the address of X in this example. The only time we ever need to store the address of X in a register directly is when we're doing pointer operations. Of pointer operations? Since we only have 3 minutes, let me show you the one from class. So we had an example here of getting the reference, getting the address of X. So the assembly code here is this. So we get this is the reference, so we're actually going to compute the address of X. So this is starting with RBP and then subtracting having an instruction that subtracts the offset. Now RAX holds the address of X, and we store it into T1.
So you don't subtract by the offset in the beginning. You do it once you store it into RAX.
So this is the distinction between pointers and non-pointer usages. So when it's not a pointer, the machine will do this computation for us. The machine will do this computation for us with this argument. When we're dealing with pointers, if we want the reference, we have to compute that, generate code that will compute that. When a variable is a pointer that already holds an address, then we can just use that data in that register. So for instance, for this, where we dereference T1, that is, you go to its address and get its value, then this is what the code will look like. So we get the value of T1, which holds an address, it's an RAX, and then we dereference that address to get the value at that address. So this is getting the value at the address that points to X. I don't know if that helps, but we only have 1 minute. It looks like there's another class that is very eager to come in. Yeah, one more, yeah.
What I've been seeing this in the pages, but like you have like diagram parentheses. What does that mean?
Oh, it's note for me to draw on my whiteboard. So it's not a good link, but it's, if you look at the board, this board thing here, that contains those diagrams. It's really an instruction to me.
Is it like meant to like embed it?
No, it's just a reminder to me. All right, everyone, have a good break, and we'll see you next week. Or actually, come to office hours. I have office hours now, so.